This semester at Clemson, the Electrical and Computer Engineering Department has collaborated with CAPER to sponsor an industry project to give students real-world experience. Power grid operators and engineers are constantly modifying transmission, distribution, and generation systems. With constantly increasing load due to innovations in technology, it is important that maintenance, upgrades, and new construction can all be accomplished without compromising safety and reliability for the rest of the system. Caper, in collaboration with Dr. Hassan Raza, Dr. Ramtin Hadidi, and Dr. Andrew Clark, has provided us with case data for a 118 bus system to analyze power flow for a set year with a set of required outages. The goal of this project is to simulate a power system and optimize the scheduling of the required outages with regards to certain scheduling and time constraints. This is a two-semester project. This semester's focus is to simulate the power system with an interactive graphic user interface to allow next semester's teams to focus on optimizing the scheduling.
Here we have our GUI. As you can see, there are two tabs, the outage selector tab and the data tab. In the outage selector tab, you choose what outages you want to run the simulation with. For example, we're going to run outage 1, 3, 6, and 14. Down here, we can choose what time we want the outages to start. Some have built-in limits based on the conditions of the outage. For example, let's make this run on the 19th and this run on the 6th. We can also press Display Outage Map, which gives us an overview of how the simulation and the system would look like. Here's the Data tab. Here we can choose a start date and an end date for the simulation. We can also choose what time we want the outage, what time and date we want the outage to display in this window right here. Let's say December 1st at 8 a.m. We can also choose if we want the simulation to run hourly or daily. Then we could choose Run Simulation. The GUI creates 3 Excel files, which are then processed in the actual MATLAB simulation. The first file is called Required Outages Demo. This contains what outages we selected and some basic information about them. The next file is called Outage Date. This gives what date we've chosen to run these outages. Finally, the date time Excel file contains what date the simulation will start at, what date it ends at, a number determining if it runs hourly, 1 for hourly, or 24 for daily. And finally, what time you want the outage to display in the window. Here is the MATLAB simulation. As you can see, we do some simple clearing before finally loading in various Excel files, either created from the GUI or given to us by Caper. After all these files are loaded in, we process the dating information for the starting and ending interval. We then process the generator outages, process the line outages to make them more readable for the simulation. We then start the main for loop of the simulation. We start time, interval, and end time. We create some basic variables like time that just tells us what time the hour is. And then check outages. This function process the outage information for that time. So for its first time, the first date and the first hour of the simulation, it will check if there's an outage at that time and then change the case file as needed. We then change the load to more accurately represent that hour. And then we run the OPF simulation. OPF is used because it allows us to make a block dispatch more easily. Block dispatch is simply how the generators are allocated to create power for the system. After the simulation is run, we check our results through some basic checks, like testing our total losses, if the simulation failed or not, things like that. We then run n-1 contingency. This simply means we're checking to see if one extra line goes down, does the entire simulation fail? Finally, this check determines if the exact hour and date that the simulation is currently running is the same one as is displayed in the data window. N-1 contingency works, but there are a few errors in the current iteration. For example, transmission lines that go down can sometimes create islands. Islands are simply buses that are isolated when a line goes down. This doesn't have any special considerations in the current iteration. Another problem with N-1 contingency in the current iteration is the slack bus. The slack bus is typically the largest generator and is used as a base for all the other buses to process their numbers around. When this goes down, the current simulation runs an error. This will need to be changed in future iterations. The MATLAB simulation creates two files as outputs. There is an Excel file for this specific date, which will then be processed by the GUI, and finally a text file, which basic information about every hour that's run in the simulation. This is one of the output files. This is an Excel file with all the bus, generator, and branch information about the time and hour we selected to display. We have power, reactive power, voltage magnitude and angle, and other information. In the generator, we see which generators are creating power and their reactive power as well. With the branch, we see basic branch information about where power is flowing and so on. This is the total output text file. For example, it gives you information about what date and time the simulation is running at this time. It gives you the total losses of the lines. And finally, some basic information about N-1 contingency. These are all branch failures. This is due to islands, as mentioned earlier. If there are other problems in the simulation, such as buses having too high or too low a voltage, or transmission lines being overloaded, that information will also appear here.
Some of the challenges we faced when designing this tool included issues with N-1 reliability, such as some of the branches failed no matter what, and issues with the system slack bus or generator 30 caused N-1 reliability to fail every time. We were able to get around this by just not toggling generator 30 when running N-1 reliability checks. Block dispatch also caused some problems, but we were able to work around it using OPF, which runs power flow in the system differently, causing it to check each bus as the slack bus, which is not normally done in the usual run PF function. Another issue we faced were we wanted to implement an outage map in the GUI that displays the power system with the selected outages, but due to the limitations of the function plot MPC, which generates the power system map, we weren't able to display the outages, but just the power system. Some more issues that we faced were communication between the GUI and the simulation. We use this using Excel sheets, which caused some issues with data types between the two, such as date time, which if you send it to an Excel sheet, it displays a date time, but once you take it out of the Excel sheet, it's a completely random number. We were able to fix this in the simulation, but it caused sometimes. Also, some of the apps that we wanted to use for the GUI were custom apps, but they could not perform the desired function, so we had to revert back to the included apps in the MATLAB app designer. In conclusion, this simulation did not run as fast as we wanted it to. It takes about 20 minutes to run one full week of data, and in order to run the entire year of simulated data, it would take much longer than that, probably about a couple of hours. Possible fixes for this would be utilizing multi-threading or a different program other than MATLAB, which utilizes multiple cores instead of single core. Also, for some options in the GUI, Python may have been a better choice as there is more flexibility there, and that would also solve any problems with the data types as we experienced. We hope this tool can be properly used next semester to optimize the scheduling of simulated outages using machine learning or any other method that the group may research.